Hi guys, welcome back to Functional Analysis. We started our discussion of Banach spaces, and so far we have assembled quite a few examples, particular sequence spaces. We have talked about continuous functions on compact intervals equipped with various norms, and the last example was about the dual spaces. Now, examples aside for a little while, now what we will do is we will develop more theory, and we will begin with a test that will allow us to decide whether a given normed linear space is actually complete, aka a Banach space. Okay, to state this test, we first need the following notion. A sequence of elements in a normed linear space is called absolutely summable, well, if this sum here with the norms is convergent. So in a sense that corresponds to absolutely convergent sequences that you know from real or complex analysis. But here it's formulated in general normed linear spaces, right? The second concept is the notion of a summable sequence. Well, that just means if the sum of partial if the sequence of partial sums, so you truncate here at capital N, if that has a limit in the space as capital N goes to infinity. That's what we will call summable. All right, now here's the test. So a normed linear space, either over the complex or real number field, is a Banach space if and only if every absolutely summable sequence is summable. So that might be a bit surprising. At least it was for me when I learned it for the first time, because it's something that you're not quite aware of when you do real or complex analysis, right? Because there what you know is, okay, absolutely convergent sequences are convergent, but you never realize that you can actually use this as a test, whether the underlying field is complete or not. And then that's precisely what it states here, right? You can use it. All right, so to prove it, there will be two directions. First off, we will assume that our normed linear space is complete, then take an absolutely summable sequence and show that it is summable. Okay, so if X is a Banach space and Xn an arbitrary absolutely summable sequence, well, apparently I have to say something about the limit of the following object. Then with y capital N, just a partial sum, I have to show that this has a limit as capital N goes to infinity, and the limit is in the same space. So then for capital N above M, say, and arbitrary epsilon positive, so yn minus ym. Okay, then the typical thing happens. You subtract off the first m terms, the remaining ones stay, and now you use the triangle inequality, and you end up with n capital M plus 1 to n xn. Yeah, but you see this quantity by the Cauchy criterion for a convergent series, because this is convergent, because you assume that it's absolutely summable, just compare the definition above. That guy you can make as small as you like, provided M is sufficiently large, right? Consequently, we are facing here, or we are dealing with a Cauchy sequence, and of course in a Banach space those are complete, those are convergent. Consequently, yn is Cauchy, and thus convergent in X, meaning that sequence xn is summable. Just compare the definition, what it meant for a sequence to be summable. Okay, so that's the easy direction. Now the converse direction. Conversely, suppose that every absolutely summable sequence is summable. Now how do I show that my space is complete? Conversely, suppose every absolutely summable sequence is summable, and pick an arbitrary Cauchy sequence. An arbitrary Cauchy sequence. Let's say again xn, n running from 1 to infinity. Okay, now let's use the definition of a sequence being Cauchy sequence. For every epsilon positive, you can find capital N such that blah blah blah. So now let's here be a bit more concrete. Let's choose epsilon as 1 over essentially j squared. So for every natural number j, we can then choose an index nj, the natural numbers, such that this difference xm minus xnj, well, is less than epsilon, and here epsilon will be, as I said, 1 over j squared. Okay, and this is true whenever m exceeds nj. This is really the definition of being a Cauchy sequence. I just denote my epsilon as 1 over j squared, and then the corresponding small n is also indexed by j, right? Good, and we may assume nj is an increasing sequence. Okay, in turn, for every j natural number, so what do I have? xnj plus 1 minus xnj does not exceed 1 over j squared. Okay, this is again, you could have started with this inequality right away, right? Because the Cauchy criterion just couples arbitrary two indices m and n, saying when they are large enough, you can get the difference of xm minus xn as small as you like. So you could have just chosen from the get-go m as nj plus 1 and n as n sub j and get that difference as small as you like. Here you will see, because we're dealing with summable sequences, we want this with 1 over j squared. Okay, so there's nothing going on here. It's just exploiting the definition of a Cauchy sequence. So, but what does this mean? So the sequence of those difference terms, x and j plus 1 minus x and j, now I run my j from 1 to infinity, is absolutely summable. Right, absolutely summable means you look at the difference in norm, you sum out the j from 1 to infinity, and you need to get something finite. Yeah, but since these are all bounded by 1 over j squared, you're dealing with a p series with p equals to 2, and that guy is convergent. Okay, so this sequence is absolutely summable, thus, and now comes the only trick that we use here in this proof, well, the telescopic sum allows me to write down this identity, j1n x and j plus 1. Now this is the reason why I want these indices n, j to be increasing in j, because then the telescopic sum tells me that this here is true, n plus 1, right? Right, so this you just check. So the j equals 1 in the sum gives you x sub n2 minus x sub n1, and that's why you have the lone sum x n1 here, because it will be subtracted off from the first term. and then they crosswise they go out, and then the one that survives is the top index when j is equal to capital N, and there survives the x sub n and then sub capital N plus 1, and that's precisely what's written here on the right. All right. So you have this, but remember, right now we are dealing with the direction where any absolutely summable sequence is summable, right? So this means in particular by assumption when n goes to infinity, or maybe I should just say is convergent when n goes to infinity, because we constructed an absolutely summable sequence, so by assumption that thing is summable. That means precisely that as capital N goes to infinity, that thing is convergent. Yeah, but this term here out front, the first one doesn't depend on capital N. So what this means is when capital N goes to infinity, that right term has a finite limit, right? So let's write this. Thus, this thing converges in X as n goes to infinity by assumption. So what have we just shown? In summary, the arbitrary Cauchy sequence xn has a convergent subsequence x sub nj, j1 to infinity. Yeah, now we use a result from the metric space module that if a Cauchy sequence has a convergent subsequence, then the Cauchy sequence itself is convergent. Okay, this is a consequence of the triangle inequality for the metric. Has a convergent subsequence and is thus itself convergent. All right, this shows that my space is complete, and since I'm dealing with a normed linear space, this just means that X is a Banach space. Okay, that's the end of the proof. All right, so you can use these summable and absolutely summable sequences to detect whether your space is actually complete. All right, good. Now, before we apply it, and we will, we need a few more things. So the first one, definition, that's an important definition now. So let X and Y be two normed linear spaces, and T a bounded linear transformation between the two spaces, a bounded linear transformation. Okay, now we say that T is invertible or an isomorphism if there exists a bounded linear bijection that we will denote by t to the power -1. This guy will go in the reverse direction, so from y to x, such that, well, it forms a two-sided inverse. So t -1 is the identity on y in that order, and if you go the other way, t -1t is the identity on x. Okay, so here the emphasis in this definition lies on this word. Okay, so unlike in, say, linear algebra, well, there everything is bounded because you're only working with finite dimensional spaces. There you just say a linear transformation is invertible if it is bijective, right? So here it's more. We say it's invertible if there exists a bounded linear bijection. Okay, so boundedness is built in there. Now, earlier on in the Hilbert space chapter, we had a notion of Hilbert space isomorphisms, right? Those were those linear bijections that preserve the inner product. Yeah, but this definition, this aligns nicely with this one, because if you have the inner product preserving nature, this was something of this type. You can look up in your notes. If you take y is equal to x, then of course this guy implies this one, right? And that in particular shows that u is bounded, right? So this is naturally built in the definition of the Hilbert space isomorphism of the unitary map. But here we're in more general setup. We're just dealing with normed linear spaces, and we want to make sense of a bounded linear transformation being invertible. And that means there exists, well, this t minus 1, which is linear, bijective, and also bounded. Okay, that's important. Good. Let me write one more thing here. So here I said it in words, but maybe let's write it. So this I sub x, respectively I sub y, denotes the identity map on, well, x respectively y. Okay, we say, and that we used in the Hilbert space chapter when we proved, that result about separable Hilbert spaces. We say x and y are isomorphic if there exists an isomorphism T Lxy. Furthermore, this ties back to that unitary map there, a linear transformation T Lxy is called an isometry. Well, you can guess, because sort of iso and metry, what could that mean? Well, that it preserves the metric, so in this case the norm, if txy is equal to, the norm of x for all x in x. Okay, so these are the norm-preserving linear transformations. Obviously, the norm-preserving linear transformations, the isometries, are injective, right? Because if you set this guy here equal to 0, remember we're dealing with linear maps, so to check that something is injective, you just have to figure out whether the kernel is the 0 subspace. So if you set t of x equal to 0, then here the left-hand side is equal to 0, but then this just means that the norm is 0, so x is 0. So that in isometry is always injective. However, in general, it's not surjective. Okay, so you cannot, in general, conclude that any isometry is invertible. Okay. All right, good. Now let's make a remark about this definition, a very important one, which clearly sets it apart from the finite dimensional world. So remark. And later on, in a couple of weeks, we will have a very big theorem that addresses this remark further. So an invertible T is always bijective. However, not every bijective T is invertible. Okay, and that is because we build the boundedness of the inverse into our definition. Okay, and I will give an example for that. So an invertible T is always bijective. However, not every bijective T is invertible. And that is certainly different from what you are being taught or what you learn in linear algebra. Right? But there again, now we know more because linear algebra only deals with finite dimensional vector spaces. So all these bounded linear transformations are, all the linear transformations are bounded. Okay, it's invertible since t minus 1 might not be bounded. Okay, I will give an example. All right, so consider the space X, C0, N, on one hand with the 1 norm. That guy is not a Banach space. This was an example. This was the first negative example. We proved that C00, 0, which is, by the way, the subspace of L infinity. These are sequences with only a finite number of non-zero terms, right? And we showed that that guy equipped with any p norm, p away from infinity, is not complete. However, it is complete if you equip it with the infinity norm, and that will be our target space. So we look at this guy and the linear transformation from x to y, well, the identity. So t of x is just mapped to x, okay? Note, this guy is well defined because when you have a, I said this when we discussed that negative example, when you have a sequence in Z00, then that sequence is in any LP space because only finitely many terms are actually present. So all these sums are finite and also the supremum is finite. So this map here, Txx, is well defined, okay? Moreover, is it bounded? Well, it is. I essentially just gave the explanation because all those sums and the suprema are finite because you have only finitely many terms. So the supremum of Tx in infinity norm, because I'm mapping into the y space which is equipped with the infinity norm, and if you optimize it over the ball in the 1 norm, then this is also finite. Again, for the same reason that I just gave. This Tx infinity here is precisely, well, the infinity norm. Infinity norm. I said it correctly. I wrote it wrong. It is the, wait a second. Yes, it's the infinity norm of my element x. Okay, good. So we have bounded. Okay, it's also linear. I don't think I have to say anything about this. This is the identity map here after all. And it is linear. It is bounded. Now we will check if it is injective and surjective, but this is also trivial. So since it's linear, again, I just have to check that the kernel is trivial. So if t of x is mapped to the 0 vector, yeah, but then by definition of the map, x is equal, well, to the 0 vector, right? So t is injective. This here, this 0 being the 0 sequence, right? Good, so that's injective, and since any x in Z00 n is of the form, well, only finitely many terms are non-zero, so you might have, you know, some non-zero, already some of those could be 0 here out front, but then at some point, and not everything to the right of that will be equal to 0. Okay, so this is clearly an element in all these LP spaces, so in particular in L infinity and L1. And now, how can we show that map T is surjective? Well, so for some and not natural number, we can use, well, t of x is equal to x and conclude that t is surjective. This is trivial. I mean, you just take any sequence in the y space. You only have to realize that the y space being equipped here with the infinity norm, it also means that that element, because of the space, is also in the 1 norm finite. So, and then you're done. Okay, so it's surjective. Altogether, T is a bounded linear transformation from X and Y, and it is a bijection. However, it is not invertible in the sense of the last definition. Okay, so let's check that the inverse is not bounded. The inverse, well, the inverse we can compute easily. Let's call it S. It goes from Y to X, and it equals, well, no surprise here because you're dealing with the identity essentially. So S of X sends the element X just to X itself. But S is not bounded because for if, let's look at this element xn, so we have n over n, n minus 1 over n, n minus 2 over n, all the way up to 1 over n, and then I truncate, and everything after that is equal to 0, and a natural number. Okay, then claim is this is an element in the Y space. Well, clearly, because it truncates after finitely many terms, so that is certainly finite in the infinity norm. And we also have that the infinity norm is not only finite, we can actually compute it. The largest term here is, of course, here the first one, right? N over n is 1. All the other ones are smaller than 1, right? So infinity norm of that guy is equal to 1. However, if you compute the 1 norm of this one, well, then easy calculation, k1n, the 1 norm is the sum, all these terms are non-negative, so you don't need any absolute values or complex moduli, you get just the sum of these first entries, which are of the form k over n, and k goes from 1 up to n, right? And what is this? Well, this is the sum of the first n natural numbers divided by n, so this is 1/2 n plus 1, right? And of course this, as n goes to infinity, becomes unbounded. Okay, in turn, so T is not invertible, right? Because the inverse, that map S, is not bounded. Okay, as I said, later on there will be a big theorem that will help us understand why, you know, this example here is bound to fail, and this has something to do with the fact that I said early on, namely, if you look at these two spaces, we checked that this guy is a Banach space, but this one here, the first one, is not, and that's the reason why this example has to fail, and that will be, you know, quantified later on by a big theorem. Okay, I will stop here. I will see you in the next video.